Good morning, everybody. I think you guys can hear me well, hopefully. Yeah, thanks for the invitation and the opportunity and also the flexibility to switch talks. Sorry for those of you who didn't want to see me in the morning, but that's what's happening. So in thinking about the title and the title of this program, I asked myself, let me just rephrase it and see what it is. And then well, I asked myself, what are the root causes that really leading to advancements in programmable quantum dynamics, which in turn, it sets the future direction we are going. And I came up with this honest answer that for the experiments that I'm about to cover is mainly experimental and hardware advancement that happened in our group in the past few years. So it's not going to be a KITP exactly, it's going to be a little on KIEP. But let me just be more specific. For instance, if you recall in December 2024, Google Quantum AI announced the launching of a new processor called Willow. And with that, in fact, my colleagues claim that, we are not in Kansas anymore, which we think about it is not actually very surprising because California is not in Kansas. But when you actually, what they meant by that is that after 5 years of hard work, we have been able to move the metrics of performance a little to the left. So what you see here on the horizontal axis is single qubit gates, 2 qubit gates, or readout errors, and you see the difference between Sycamore and Willow. And oh, sorry, what happened? Oh, I'm missing something. What happened? Oh, I accidentally erased a slide. I don't have it even in the deck. Okay, well, you just have to take my words for it. So basically, it means that lots of work has gone into to improve the, maybe I should keep an eye on the slides too. To push the metrics of performance, and even not by one order of magnitude, a little here and a little there, and you can see there's some improvement. And then we visited a problem that we had visited 5 years ago. So you see October 2021 and October 2025, we come back to the exact same problem, which may not be actually so much novelty for theorists, but actually what we are trying to show in here is that even in this problem, when you have a very powerful hardware, now you can do things that you could not do before. And with that, I want to, well, the work is out. I mainly talk about this work that appears in press a few days ago. And as always, it led to some whatever discussions. Some people like it, some people didn't like it much, some friends were not very friendly, and some were critics. Some said we should focus on algorithm, but not. But overall, I don't disagree with this criticism and comments. What is actually quite interesting is that science is now discussed in different journals besides physical review family of journals. That's actually a very interesting and exciting moment. And I think junior members of the community should not take it for granted. That was not the case maybe a decade ago. So that's where we are. This is the work that I'm going to talk about and was featured on the cover of Nature, but there are a couple of things I want to highlight about this work. One is that this is an experimental discovery in a sense that I will explain to you what I mean by that. And then there is a relevant to application. This is an honest-to-God effort that we made to our finding an application within quantum dynamics with noisy quantum processors. And I tell you what's relevant to the application. And then in trying to figure out this application and whatnot, we look at the computational complexity of the problem that we have created and that we are trying to solve. And I show you some benchmark of the computational complexity of this, and you see that, indeed it's not trivial to do similar problem on a classical computer. Okay? Well, I think every experimentalist introduced their platform for a few minutes, so I will do the same, just to be sure we all know what the platform is. We work with Josephson junctions. They are many, many decades old, and you can see the processing, making of the qubits, making of our giant atoms start by evaporating a piece of aluminum on an inert substrate, could be silicon, could be sapphire, and then oxidizing the whole area, the whole chamber essentially, and then depositing another layer of aluminum on top of it, and you form a junction about 200, 300 nanometer in each direction, and about 5 nanometer separation by oxide. And you make two of them, which is harder to see in here, and then you shunt it with a capacitor. By doing that, you make a nonlinear oscillator, and this nonlinear oscillator has a nonlinear energy spacing, which allows you to address individually. And this concept of quantized energy and whatnot, as you know, was the subject of the Nobel Prize announcement a few days ago. But what we do, we put lots of these things together. Maybe in this example, which actually was constructed, built in this UCSP clean room more than a decade ago, you can see we have qubits, 9 qubits in this case, and they are coupled with a coupling element, which is another nonlinear resonator at much higher frequency. And every qubit has its own readout line. With these readout line are linear resonator, and they are slightly different in length. They're lambda over 4 resonators. And they all maybe not easy to see with your eyes, but you can take my words for it that they are slightly different in length. So we know which resonator is associated with which qubit, and the AC Stark shift in these resonators tells you if the associated qubit is occupied or not. So with one shot in a frequency domain multiplexing, you can read the state of all the qubits in one shot. You get a string of zeros and ones. And you can do that maybe 100,000 times a second, 100 kilohertz. So it's very, very fast data rate. We can, but also note in here that for every degree of freedom for qubits and couplers, we have a special wire. So we show we have full control over qubit degree of freedom and the coupling between them. So maybe I show you something about how analog evolution could look over this, but maybe we don't get a chance for it. Usually we're going to be content and doing qubit gates with them. So let's go to this problem of measuring out of order time correlations. And essentially, with the example that we get into eventually is that let's say you have a molecule and certain bond dimension or certain property of the Hamiltonian describing this molecule is unknown to you. What you could think about that you can create a dynamic under this Hamiltonian, and then maybe you come up with some spectroscopy technique to read from this local observable measurement. You can maybe try to see what happens if you tune this parameter and whatnot and get to read it. This is, in principle, is okay, but in reality, what I'm describing is kind of similar to seeing if we can create sensitivity to some initial state changes. And we know from class, this is what we do to study dynamic in classical systems. And we are usually interested to see if a tiny change in our initial states can have a in systems that have positively Lyapunov exponent, have some large consequences that we can observe. But in quantum systems, we know this simple recipe would not take over. If you have two initial states that are slightly different from each other, evolution under Hamiltonian is going to be unitary overlap conserving, and as a result of which, whatever overlap they had in Hilbert space is going to remain the same, so that's not going to work. And we need a little more advanced procedures and dynamical sequences to bring out the subtleties of the dynamic in a system. And that is where OTOC and OTOC square has been introduced many years ago by many different researchers that work in this field to study non-equilibrium dynamic, thermalization, how information is lost in black holes and whatnot. And all this would be the objects that we construct. So we have a sequence of gates, unitary gates, and then there is a perturbation, and then the inverse of those gates. In the absence of perturbation, U and U dagger cancel each other. And at the end, we ask about this correlator. Or if you go to OTOC squared, you would ask about this correlator. And being an experimentalist, I could not keep track of these U and B and M, and what I came up with is a very simple pictorial representation of this as an interference picture is nothing new. It's just a pictorial representation of what these correlations are. So this essentially, we like to think about it as a double loop interference and this one is a single loop interference. Essentially, it's just a pictorial way of talking about the same correlation function. So let me just I state the problem that we are interested in a very precise way so we understand this. We are going to construct this U by sampling single qubit rotations and entangling gates. So we're going to have an ensemble of these random quantum circuits on a 2D grid of qubits. And we are saying, can we estimate any of these correlated with epsilon error? And then the question is, at the moment that we can do that, is how is a classical computer is catching up with what we can do. So this is the statement of the problem that we are trying to do, and there is a very short write-up on it in this archive paper. Okay, make it very, very simple. Again, another pictures that emerge from this is that what we are trying to do, if we are trying to get in this ergodic dynamic at the verge of ergodicity, essentially, we are trying to focus on a conversation between two people in a very busy room, and we are trying to show you that we can actually tune to a given interaction, and we can pull that out from a chaotic dynamics. If you have not ever seen OTOC result, this is a typical OTOC sequence, how the average OTOC behavior looks like. This is from a few years old paper. So the U sequence, the unitary evolution, composed of an entangling gate and a random single qubit gates. And here I show you the OTOC as a function of number of cycles that go to U and U dagger for I-swap type choice for entangling gate or square root of I-swap for entangling gate. And you can see as time goes forward, you see two distinct behavior. One of them actually is much slower and has a diffusive OTOC front, and the other one is very sharp and either hit or miss kind of. But I'm showing you an average. That's not me, yeah? And average, by average, I mean these single qubit gates are randomly chosen, so you have freedom over there, and this is an average over that ensemble, and you can see a couple of instances of them in here. That's fine, you know, kind of maybe expected with that butterfly that I keep showing you. There is a butterfly, there is a perturbation, and you look where the front is. That's all intuitive. But what is very interesting is that we look at, you pay attention to individual circuits, meaning that you are going to change this random sequence with this recipe. There is a freedom of choice in here. And then you can see these individual OTOC signals are acting quite different from each other, which is essentially give you an opportunity to encode information, right? I'll get to that in a second. Again, the obvious part is that at early times, this perturbation has not reached to the measurement point, so this is flat. This is 1 minus the commutator of them, so it's no effect as from butterfly reached to the measurement, so it's nothing. And then at later time, it gets there and is fully information is fully scrambled and is dropped to 0. But what is interesting is in this intermediate regime between them that we are going to zoom in and focus on. So again, to show this more clearly, I'm showing you C4 now. This is OTOC squared. And you can see it has a propagating front. This is the average behavior, but the lowercase is the fluctuation in OTOC, circuit to circuit variation. And you can see, you know, white means nothing or no signal, but then there is a propagating front that we have in here. And here is, you can see, as I said, in the case of a time order correlation, that's the gray curve, you quickly damps and drop below your signal to noise ratio, or you just cannot resolve it in the experiments. But by going to OTOC and OTOC squared, we are able to slow down the propagation, so we are staying above our signal to noise. And we see, well, we like to claim the polynomial decay, but it is what it is. So we are kind of going to ride on this front of it, and that's what you are seeing here. So I mentioned that now there is a chance that we have created sensitivity to this propagation, to this front, and let me show you more clearly. The setting that we are making in here is we are going to inject a sequence, inject a layer of Pauli gates, okay? And we are going to see that if it is going to get so washed out that the final signal is independent of having an injection or not having an injection. Essentially, in the interferometer picture that I'm drawing here, we are trying to put a phase shifter in this interferometer, and we are going to see if at the end of the day, when we are doing a measurement, would we see any effect out of this phase shifter, or the whole thing is so ergodic that couldn't care less about that. So let's focus on the insets. In the inset, I'm showing that the outcome of the measurement when we have Pauli and when we don't have Pauli for C2 is highly correlated, meaning that the OTOC signal you get, it couldn't care about injection of Pauli or not injection. The value you get is remain highly correlated with each other and would not care about the injection of the Paulis. On the other hand, when you're versus with Pauli insertion, when you look at the correlation of with Pauli versus without Pauli, for the case of OTOC squared, you see a very wide spread, meaning that it would actually care if there is a minor changes in the circuit, and the circuit changes is what I'm describing in here. And the main panel is also showing the same thing for you, showing you in a logarithmic scale, so you see that there's several order of magnitude changes created. It's a bit funny because this is 1 minus something. Anyways, detail aside. So what I like to get out of this is that we are enabled to basically characterize details of the circuit. Is going to have a very visible fingerprints on the final measurement, and that's actually become very crucial for us. So before I move forward, I just want to, let's face it, we have to do the proper introduction of the subject by going to the Heisenberg picture. That's really the convenient and more meaningful more convenient framework to discuss about OTOC is in the language of propagating of operators in the operator space. But just the very simple picture associated with it is that now we're going to freeze the states and the operators are going to evolve. And originally this B, butterfly operator, is not commuting with M, but as time goes by, the commutator of them become non-zero, and that's what the OTOC is essentially measuring for you. Regardless of details, all the time you can write these butterfly, the propagation of this butterfly operator as the sum of Pauli strings. And that is what we are going to use. So what happens if you have Clifford circuits or simple circuits, what happens is that this Pauli string, a string doesn't necessarily mean a 1D object, it could be a sheet of Paulis. This string evolves into spreads to different Pauli strings when you have, let's say, Clifford circuit. But what else could happen is that in addition to spreading, there could be many sheets needed to describe the evolution, meaning that not only spreads, but also entangles. And at every instance of time, you need lots of Pauli strings to describe where your Pauli operator is. Pictorially, I can also show it in this pattern. You start from one Pauli string in the Pauli space, and after several cycles, you can see that it comes to many Paulis that you need to keep track of. So this is a good representation, but the challenge is that now we have to figure out how many of them to keep track of. A priori is not clear which one you could drop. So again, yeah, this formalism allows us to know what we are after, but that is not sufficient, because if you want to do this sum completely and you don't know which one to drop, you're out of luck. But then if you drop, you might create mistakes by not knowing how to approximate these ones. When it comes to OTOC, you see what matters and what contributes at the end of the day, what we call the small loop interference. Means if Pauli strings are evolving far from each other, you can be sure they're not going to come back to each other, and you can ignore them. But Paulis that stay very close to each other in this Pauli space spreading and have a chance to come to each other, they are forming what we call a small loop interference, and that's what you need to keep track of. So this is a very enabling recipe that helps us to keep track of Pauli's and then keep the computational manageable. However, when you comes to OTOC squared, there is not only this contribution, there is another contribution which is harder to keep track of, and that is the experimental discovery that came out of this. We realized that when these Pauli operators have these, Pauli strings have these very non-trivial algebraic relation, which is not easy to a priori know which ones to keep track of, they have a major contribution, and we call it large loop interference phenomena, and that is part of, goes into forming the C4 correlation. So you need to keep track of two things. And one of them, being the small loop, is easy for Monte Carlo to help you and carry on. So you see C2 in here amplified by 100 times. Experiment and up to a certain point, exact simulation and Monte Carlo simulation are all agreeing with each other without any problem. But when we come to particularly estimating the off-diagonal component, as I described in here, to OTOC squared, you can see that the Monte Carlo starts to fail, and we kept it at the level that we could do exact simulation. You see experiment stays with the exact simulation, but Monte Carlo starts to fail because it's not very trivial to hunt and find these large loop interference pictures. And the claim of the paper is that let's go take this concept to up to, let's say, a system of 65 qubits. We go to 65 qubits, and these are instances of measurement. There's no particular relation in this axis. There's just random instance of measurements, and we have a good hold of the signal to noise estimate of our system, so we know how precisely we are measuring each one. And note that we cannot put an exact point at the level of 65. And here a time estimate of what it takes to do that part. And this is the claim of 3.2 years that you see in the manuscript, which is saying that to do this point, according to us, this is about 1,200 cores in a frontier. This would be the time it's needed to do. So obviously we have not done it, but that's what we are claiming is the cost of doing this calculation. Okay. But let me step back and say what is the meaning of this work so far. In terms of the problem, computationally complex problem that we are solving here. If you recall the bit string sampling, or the other work we did in 2019, we start from a product state or some simple state. We evolve it with some unitary operator, entangling gates and whatnot. And we measure a bit string, and we repeat this experiment many, many times. That's the old work. And sure, we can very effectively sample these bit strings, but then there is no way to check, or there is no way to verify that that you're going to get this same bit string if you run the experiment again, or there's no easy way of these strings are not going to repeat themselves, because usually you're dealing with a Hilbert space. On that case of supremacy experiments was 10 million billion dimensional Hilbert space. And this, but then you're maybe sampling 1 million times. So there's no way of verifying that if a given bit string is correct or not. So it's very challenging in that sense. However, in this local observable problem that we defined in here, you're measuring a correlation function. And sure, it's very quickly, you can solve the problem of saying what expectation value is. But also you can verify it. You can pass the circuit to someone else and say that we have done this. At least quantum computers can do this. So in that sense, I was told that we are falling into very different computational complexity classes. In particular, this is falling in BQP, which can be mapped into a decision-making problem. So in that sense, is a very different problem. So and that's why some of the excitement about the works come about, and that's why we are going to I show you an instance of it, an example of it, that how it helps us to learn Hamiltonian. Say that you have a molecule, as I was highlighting initially, and there is some unknown bonds about it. You can do the NMR experiment, and then you can see if you can figure out the coupling and whatnot associated with it. But here, I didn't get to a molecule per se. There is another work I didn't have a chance to summarize it in here. But let me just give you a contrived version of it, but I can explain this in detail what it is actually. Let's say that, one of the gates, one of the parameters that goes into these unitaries, let's say the phase associated with these unitary gates goes in here, is unknown. And we want to know that. Of course, we set the problem that, and we are solving it, so we know what the answer is at the end of the day. But I'm trying to show you that one can vary the circuits. These are instances of the circuits that are distinct from each other by other choices of single qubit gates. And then you can define a cost function, and then cost function is minimized, where essentially the value that a priori I know what it is pointing to that value, and that is what we are saying can be used to learn properties of molecules and whatnot. In a separate work, we actually talk about that. So this is the OTOC work. Okay. Yeah, I don't know. Well, I was talking to Roderick, and we thought to present this work in here because referee was giving us a hard time, but just as of last night, it just, I don't know, we guessed the referees in this room, so maybe I just give a 4-minute brief thing. I'm going to eat up my question time. Yeah, just so you know, it exists because I heard lots about fragmentation and then lattice gauge models and whatnot. So I help you to at least be able to read this work in the future. As a result, I would not tell you the intro. It's your work, essentially. We are familiar with localization with disorder, Anderson localization, many-body localization. And for many years, we asked, can we localize in the absence of disorder? These works are goes in fact back to 1985 or so, when the people thinking about, I don't know, was it 2 isotope of helium or heavy isotope or light isotope, and then they figure out that you can have localization in systems when you have 2 very distinct masses. So there are many recipes and whatnot for understanding localization in the absence, or proposals. And we picked up on this one, which was was done at 2017. So let me just show you what the data is. Yeah, it's going to take me a few minutes. But then I tell you why. Maybe it's more important to say why to do such experiment with quantum processors, before you now come to the microphone and say why you did this experiment. So you have a Hamiltonian, and this Hamiltonian has no disorder in it. And for reasons become obvious in a second, I called qubits in 2 groups of qubit, matter qubit and gauge qubit. They're all qubits. And they are forming a ring. And this Hamiltonian, you see the parameters are outside summation. There's no disorder in it. And this gauge sequence you see in here associated with exponentiating this Hamiltonian. My point is that these are all translationally invariant. There's no disorder. The initial state also is translationally invariant. Matter qubits are plus x, either one case, or plus c on the other case. And the gauge qubits are some tilted angle, except one of them, which is fully flipped. This middle one is fully flipped with respect to other one, right? The title of the Anderson paper was Absence of Diffusion. So we are trying to create a bump in energy and see if we see the diffusion of that hump that we have created. So no disorder in the Hamiltonian, no disorder in the initial state, but yet you see a very distinct behavior in these 2 cases. You see in one case that the perturbation that you have placed at gauge qubit 10, it stays more or less where it started. In the other case, it propagates rather freely. This color plot is expectation value of this term. The second color plot is expectation value of the coupling term between matter and gauge fields. And the last one is the expectation value of energy. So you see that all of them kind of saying the same story, that this is propagating very rapidly, and it does not propagate in the other case. So what is happening in here is, got to be fast a bit in here, is that if you start from a disorder-free Hamiltonian, which you have disorder in it, you can introduce ancillary qubits, and this scalar value, which was your binary disorder in our case, can become an operator in this Hamiltonian. But since this operator now commutes with the Hamiltonian, is a conserve of motion, now you're essentially dealing with a lattice gauge with this frozen disorder in it. What I'm saying is that in the Hamiltonian that we have, it seems disorder-free, but this sigma x can be chosen, whatever value initially is chosen. It set the gauge sector you're in, and you're going to stay on the same gauge sector. If you choose sigma x, for instance, to be +1 in all cases, you would be in a disorder-free sector, such as this one. And if sigma x is chosen randomly, you would be on a disorder sector. And most of the sectors is disorder, exponentially many of them are disorder. And when you start randomly, you essentially would be in one of these disorder sectors. When you're choosing this initial state to be +c, again, your initial state is translationally invariant, but then you're in the superposition of all sectors in here. And that is what happened in the other one, and where you see, where we saw localization. This is significant in terms of hopefully maybe settling the debates in the many-body localization arguments, in a sense that now you're able to sample all disorder realizations, and you would not be questioned for missing rare events, which has been the cause of heated debates. We can continue this to 2D systems. Of course, the 2D dimensionality of us is not that big, but we can go and again do the same physics by putting a disorder imbalance in one corner and see how it propagates. And you can see two distinct behavior. You should know that you should never trust experimentalists showing you color plots. You should always ask them to make cuts in here, and we made the cuts of the same data. In here that you see in one case is very slowly coming and thermalizing because it's not a large system, so it's very hard to say if it eventually thermalizes or not, and answer the key question in many-body localization that everybody likes to hear. But at least you can set up the stage and see some early time behavior. And in the other case, you can see that, you know, very quickly when you're in a single disorder-free sector, very quickly you're thermalizing, and the hump vanishes very quickly. So why should do these experiments on a quantum processor? Is, as I said, is about being able to make the whole superposition of all sectors. So in the spirit of Grover search, which you can essentially go through a phone book in one shot, what you could define is a search, is a Grover search, and doing a phase estimation in here to arrive at the observable that you are interested in. So let's say simple case, right? You want to know the local observable in here, and you have to sample many disorders, and in order to gain confidence in the expectation value of that disorder, the number of sampling that you need to know goes 1 over error, that is you're trying to bound your local observable with squared. However, if you want to, you can leverage the quantum processor, which we have not done in this case, but I'm showing you the highlight of an idea, which you can do phase estimation. You bring several ancillary qubits, and in one shot you can essentially, within this depth you can, I think you can do one, well, I think you can get the same accuracy with shallower depths. Right? So therefore, there is some notion of polynomial speed up that you can leverage, and then by this you are essentially very reliably have sampled all your disorder realizations. Okay, I should stop in here. Okay, that was too much. Maybe I should say who actually did the work. This is the effort of many of my colleagues working at Google up the road in here. But also I want to advertise the program we have started, which we are hosting a student as an intern for an extended period of time. And you can see this batch of students who have a very fun time, and you guys are going to have a hard time getting them back to their schools now. Thank you.
Okay, questions?
Thanks for the very nice talk. Maybe a bit of a naive question. So you kind of touched on how this OTOC algorithm can be useful for NMR. Like, I can understand like Hamiltonian learning at the abstract level, but if I actually want to apply it for like actual molecules, like I guess I'm a bit confused about how like that input problem part like is going to be implemented in that like the goal is, if I understand correctly, to learn a unitary that you implement on a quantum processor. But if you don't know what the system Hamiltonian is, like, how is that unitary?
No, it's not that you don't know. You know for the most part. And there are a couple of bonds or something that is questionable. For the most part, you know the Hamiltonian. If you, in that example, I was, yeah, I think you just, if you really have, if the whole thing is unknown, it's become very messy. But to begin with, consider a case that one or two interactions are unknown to you. By mapping this Hamiltonian, now you can have an adjustable parameter that you can go and figure out. Because on the NMR experiment, you get a single number, but you don't know where it comes from. And here you can tune it and see exactly where it's coming from, essentially.
So is the point here more like learning the landscape of like the system Hamiltonian?
No, it's much more limited than that. It's really a few very well posed, sharp questions. It's not that the choice of problem has to be cleverly aligning up with the capability, meaning that you have to know the Hamiltonian for the most part, and then there are a couple of questions left that can be mapped, not everything.
Does that imply that if I don't know enough, then this wouldn't be efficiently implementable? Like, I have to ask a localized question. Thanks.
Yeah, thanks for the talk. About the OTOC measurement, would you mind to share more about the understanding of the noise on this OTOC measurement? And also, I wonder, in addition to some fundamental physics that helps you to get a strong signal from the double OTOC, does this thing also naturally remove some noise, like in echo style?
Well, I think the noise in the system.
Cancer noise, yes.
No, I don't think there is a free lunch or there is any hope for. I mean, this is what it is, right? You're fighting over signal to noise, and this is rapidly coming down, and noise would lead to washing this out and would make it to go faster. And the challenge is the processor good enough for this decay to be not as rapid? It's very easy to get zero. And the fact that these numbers survive in this very small scale is indicative of the fact that we can handle noise too. But I don't think OTOC squared just get easier and easier. It's much deeper circuit and it's much more challenging.
So it won't cancel out some noise because
only in theory land, yeah.
Okay.
Well, I mean, it does something about the coherent error, but I think the decoherence is a bigger issue.
Hey, Pedram, thank you for the talk. For the non-computer scientists, could you elaborate more a little bit on the nuances of the word verifiable? I understand it's reproducible, but what are the checklists that?
No, well, I was just repeated what I was told to say. Well, what I mean is that now let's talk physicists. We have a local observable. I tell you, I run this circuit and I get 0.73. Now you can verify that. I can hand it to another quantum processor and they can run the same circuit and we can verify it. If I run the first case, maybe contrast helps in here. If I run this case and I get this bit string and I hand it to you, you have another quantum computer, you say, I got that bit string, and we don't know what to do with these bit strings that keeps coming. In this case, is a correlator between +1 and -1, and we can measure it and we can communicate it. Let's put it this way. If we are thinking that maybe I'd make 20 circuits with different single qubit gates different from each other, and we get 20 values, and then I pass it to you and say, can you say which one comes from which circuit? In that sense, it can be verified. It's a weaker, I have a quantum verifiable, meaning that it cannot be verified by a classical. Is not as simple as, you decompose a number and then you know which prime numbers multiply to get there. It's not that. Is another quantum processor owner can verify this result. It's a little weaker notion.
Thank you.
Erika?
Yeah, I have a question about the Hamiltonian learning part. You had this cost function. Can you explain that?
The cost function was not much, except that maybe kind of some meaningful sum of these instances. These instances are distinct from each other by choices of single qubit gates that I'm now showing you. So you choose a single qubit gate, and then you sweep this theta, this green parameter continuously, and you get a curve. You change that Hamiltonian a little bit, meaning that you change this single qubit gates, you get another one. And then, for instance, you see cases that this is hitting two values, so you don't know which value to choose. And then just some squared sum of these instances give you the cost function, nothing very...
So those those three panels that you have there, they correspond to different...
Single qubit gates are different, and we have 20 of those.
Oh, I see.
Andreas?
Thanks for a nice talk. I was just wondering also regarding this, you're saying that this is towards a quantum advantage, so what's exactly meant by this? And
well, you see, first we show that you have to go to OTOC squared to slow down the dynamic, you don't fall into signal to noise. Then I showed that I can now imprint detail of a molecule or detail of evolution into Hamiltonian, and I can capture it. And then I showed that, okay, so we have made this circuit, and to the best of our capability, how long it takes to do it on a classical computer, and we came up with this number. That's what I mean. Yeah.
And yeah, sorry, Yancy, go ahead.
Yeah. Okay, so my question is, which quantity exactly do you claim that is difficult to compute? Is this OTOC 2 squared,
Yes,
averaged over the circuit or a particular circuit?
That's a good question. C4, which is OTOC squared,
Yes.
has two contributions to it,
Yeah.
and capturing this contribution is very difficult. OTOC squared, which is C4, has diagonal and off diagonal, and capturing the off diagonal of it in Monte Carlo is very difficult.
Okay, so, but to formulate a precise mathematical question, it has to be that, do you consider an ensemble of circuits?
Yes.
Yes. Or just a single circuit? Which one is difficult, or both are difficult?
No, I think for a given circuit, sorry.
For a given circuit, no ensemble average then?
No, we want to know the observable associated with a given circuit with error less than epsilon, yes.
I see. Okay, thank you.
Confused, yeah.
So thank you for the very nice talk. So I'm not sure if my understanding is correct. So it seems to me OTOC is related to the time reversal of unitary dynamics. But isn't that for unitary dynamics is intrinsically reversible already by considering the inverse? So why does OTOC like powerful given that the theory is based on time reversal of unitary dynamics?
Well, it doesn't fully cancel each other, right? If these B's were absent, then you get nothing. Then you fully steer it back. But there is a B. But what I'm claiming is that by going forward and backward, I would do some echoing, similar to spin echoing, that enables us to catch very details that we are interested in, such as listening to some tiny bit of the whole thing. By placing these in a proper place, you can really tune to a particular interaction. Am I making sense?
So it's like you put a B between the forward and backward.
Yes.
Then you have
Okay, I guess we're on time, so let's break here. Let's thank Pedram again. And now it's coffee break. We'll reconvene at 11.